So in this section, I'm going to present convolution, giving a 1D example, and also demonstrating matrix vector notation, which I think you'll find is very useful for having a very comprehensive understanding of convolution. So as we'll see as these slides unfold, we can consider convolution either as a weighted sum of columns of a matrix, which I much prefer in my understanding of convolution because it naturally fits with the imaging sciences. However, it can also be useful to understand it as a scalar product where we just go across the rows of a matrix. But all of that will become clear as we move along. But just to emphasize from the outset that convolution is actually a very straightforward concept, and so I really hope these slides will convince you of its simplicity. So, at the outset, I just want to re-emphasize how we can deal with a function, and it's in discrete form. So here I'm plotting a continuous function, f of x, just the independent variable x, giving a response value f for a 1D function. And we can consider a discrete domain version of that function by using now the square brackets to indicate these are discrete samples. And again, sampling will be covered elsewhere, but here we just want to be satisfied that we can have basically a list of numbers to represent a 1D function when we have a discrete independent variable x. So here I'm just showing example numbers that could capture all of these various samples of that continuous function. Okay, so instead now of dealing with this continuous function, we're just dealing with this series of this sequence of samples which I can just stack into one tall column vector, quite a high dimensional vector, the number of dimensions of course corresponding to the number of elements, but we're just representing a 1D function, a 1D discrete function. Okay, so this is just the starting point for a good grasp on convolution. So now to get on with convolution, what I'm going to be doing is taking a very small input function. So this is my discrete function f of x, square brackets for discrete independent variable x, and I'm just going to consider the case of 5 sample values. And as you can see, I've stacked them into this column vector 5, 3, 7, 1, and 2. That is what I'm going to call the input function. I'm then going to convolve that with this function here, which I'm going to call h of x. Ignore that minus for the moment, just consider this as h of x. And when we're dealing with temporal or time-based signals, this function h is referred to as the impulse response function, and that will become clear as we go along. If this were to be a spatial function, such as an imaging kind of system, then that response function would typically be called the point spread function, or PSF. Sometimes it's called the point response function because perhaps that's a more logical name for it, but convention tends to be that we call it the PSF. And so I'm only using a very small function here, just example values of 3, 2, and 1, and then zeros elsewhere. So for convenience, I'm just placing that also into a 5-element vector, 3, 2, 1, 0, 0. So the task I'm going to demonstrate over these next 2 slides is how to convolve this 5-point input function with this 3-point response function. Okay, so step 1 is we just visit each of the values of the input function. So we're going to start at the first sample point. So I'm going to go basically along the independent variable x. I'm going to start at x equals 0. So that's what I've got at the top left here. The function f evaluated at x equals 0. And we know from this description here, it's just a value of 5. Okay, so that means we take 5 lots of the response function, because we can consider this input function as just a series of deltas or a series of impulses, a series of points. And this function h is the response to each and every one of those delta functions. So therefore, we're visiting the first point or impulse or delta function, which has amplitude 5, which means we need 5 times the response function. Okay, and now the response function is just h of x, and it's got effectively no shift. It's already centered starting at the very correct point of x equals 0. So we take f of 0 times the response function, h of x, and that gives us the total system response to that first sample of the input function. We then proceed to the next sample. So the next sample in the input function is this delta function here, which has an amplitude of 3. And that means we take now 3 times that response function. Okay? So here we go. We're showing that at the top left here on the second row. So we're saying we take the function f, evaluate it for an input x equals 1. That gives us some overall constant value, a coefficient, for the response function h of x. However, the h of x needs to be shifted to the position of the sample, the position of that input function's delta at that point. Okay? So therefore you'll notice that this response function was shifted along. So I've been lazy, I've just kept that the same on the right hand side, but if we were to write it out, it would be 0, 3, 2, 1, 0. Okay? And then we proceed to the next delta function. Okay, so now you hopefully saw that shift again. And now the third value in the input function is just a delta function of amplitude 7. So therefore, we've got the function evaluated at x equals 2. We know that that is a value of 7 because x starts from 0. Value of 7 multiplied by the response function, h of x, but shifted to the right by 2 samples. Okay, and so that was the h of x function shifted to the right. And then we proceed on to the next one. The next sample is located at x equals 3. And then, so we plug in x equals 3. We find the function value f at x equals 3. So there's f of 3. And we know that that's going to be a value of 1. Okay, so f of 3 when evaluated is equal to 1. And that's multiplied by h of x shifted to the position of that sample, which was x equals 3. And then to finish, we then move the response function again to then see what the response is from the last sample. And we know that the last sample is just a value of 2, a delta function scaled by a value of 2. And that's the function f evaluated at x equals 4. So therefore it's f of 4 multiplied by h of x shifted to position x equals 4. And then all we do, because this is a linear system, and we'll get into linear systems later on more explicitly, but because it's a linear system, all we have to do is add up all those individual responses to all of the individual delta functions. So I've got this big capital sigma for summation. And if you add together, so you just basically look at G1, G2, G3, all the way up to G5, and all you do is just scan down here and just add up the net result of the delta functions as you go. So if you add that one to that one to that one to that one to that one, just a very simple bit of addition, then you end up with this overall output, which is the output of the convolution, that is the convolved result, g of x. And so you'll see that written now, hopefully in a very logical way that should be clear to you now, where all we're doing is saying the output of the convolution is just the input function f evaluated at each and every possible sample point. So we just use this summation index k. We just use k to visit all of those x values. Okay, so we're going from k is minus infinity to plus infinity, but we know the samples that are in the negative area or beyond the sample value of 4 are all 0. So effectively this summation is only over those 5 values where we have a non-zero function. So we just evaluate the function at those points, and at each point treat it as the coefficient or the weighting factor for the response function shifted to the location of each and every one of those delta functions. And when we do that summation, we get the output, which is convolution. So that is all that convolution is, nothing more, nothing less. What else do I want to point out on this slide? Just to emphasize again that the function h is called an impulse response function if we're dealing with time-based functions, and it's called a point spread function if we're dealing with spatial functions. Now here, because I've been using x, that is normally suggestive of a spatial function, something that varies along a spatial position x, but of course it could be f of t or something like that if it's a temporal function. So I now want to go to the next slide and show you this now in a matrix vector context, which will hopefully give even more insight as to what's going on in convolution. So here we go again. This is the same input function, okay, the same sample values. And what I've done is I'm showing the sample values here at the top right corner in a vector. So 5, 3, 7, 1, 2. That's 5, 3, 7, 1, 2. That's the input function. And then I'm showing the function that I'm convolving it with, that response function, the impulse response, the point spread function. I'm showing that now in shifted copies in columns of a matrix. Don't worry, this will be clear as we go along. So there are the sample values explicitly listed out as 3, 2, 1, 0, 0 for the response function. So first of all then, as we know from the previous slide, what we do is we visit each and every sample in the input function. So the first sample value, so x equals 0, the function f is equal to 5, which means we take 5 lots of that 3, 2, 1, 0, 0 response function, which is in the first column of that matrix. Okay, so 5 times that is what I'm showing on the left-hand side here. So it's 15, 10, and 5, and then 0, 0. And I'm just showing the overall response to that single impulse input of amplitude 5. Then, as we know, we visit the next delta function in the input function, and that's delta scaled by 3. And then that scaling factor is then used for a shifted copy of the response function, because the response function needs to correspond to the location of the impulse that is causing that response. And that's now located at a shift of x is equal to 1. It was shifting by 1 sample. And so that means this would now be 0, 3, 2, 1, 0. And that's what I'm showing explicitly in that column. And there is the result of 3 times that column. Okay, so 0, 9, 6, 3. It's just 3 lots of that response function. And then we visit the third sample in the input function, and so that's a delta with amplitude 7, which means we take 7 times that column, where that column now is the response function shifted again, this time to correspond to the location of that third delta function that we're considering. And so that will look like the plot on the left-hand side there. And here it is written out explicitly, 0, 0, 21, 14, and 7. And then we carry on again to the penultimate sample here. So that's a value of a delta function scaled by 1. It means we take a weighting value of 1 of that penultimate column, which will give us this scaled response function. So notice here, for convenience, I'm clipping off the values of the impulse when they go beyond my range of consideration. And that is fine for convolution. There are different ways of handling it. And later on, when we get to Fourier analysis, I'll be showing that actually it's important to deal with periodic functions where these responses would lap back around at the top. But those are different interpretations and uses of convolution. They're all valid in their own ways. Here I'm showing you the simplest form, where when the signal goes outside our range of interest, then we just don't see it. Okay, so, and then finally the last sample, we know that it's a value of 2 for a delta function there, and that means we take 2 times that last column there, and again it's only capturing the start of the impulse response function here, because the rest is going outside my field of view, if you like. And so here I'm showing therefore 2 lots of that response function. So that's going to be 0, 0, 0, 0, and then a 6, and then the other 2 values go beyond our range. And then what we do, you should realize, of course, is that we sum up all of those responses to all of those delta functions. And so I'm calling that a weighted sum of columns. What we've done is looked at this matrix. That matrix just contains shifted copies of the response function. And then we're weighting each of the columns by the values of the samples of the input function. Okay, so that's what I'm showing there. I've just taken all of these those G response functions, added them all together, and that gives us the output vector, which is the result of the convolution. And that is nothing more than matrix vector multiplication. So now I'm here explicitly plotting the output of the convolution, g of x. So that's 15, 19, 32, 20, 15. And so I'm just showing the peak value there. Right, so hopefully I've convinced you about the simplicity of convolution. It's just a weighted collection of shifted response functions. However, many teach it a different way, which is perfectly valid and completely equivalent to what I've just described. So if you like here, I've been adding together the response functions all in parallel, if you like, considering all 5 output points simultaneously. What you could do instead is just say, well, okay, and that's what I'm highlighting with the red here. I could say, well, what if I'm just interested at this sample point here? So this would be x equals 0, x equals 1, 2, so this third sample point here. Then we can see by matrix vector multiplication that that is just corresponding to taking 0 times 5, 1 times 3, 2 times 7, 3 times 1, and 0 times 2, just adding them together, just doing what's called a scalar product of 2 vectors, because this is just a row vector and this is a column vector. And so that would often be written in this way here. Now, that's fine, that's just a mathematical evaluation of finding one output element of matrix vector multiplication, but take a look at what that function looks like, that row vector here. I've plotted it here. Take a close look. Think about that just for a couple of seconds. What has happened to that response function? I hope you can recognize that it is a reversed response function. Okay, when we started out, we saw those arrows dropping. If you look down one of the columns here, it was going 3, 2, 1, 0, 0. But as we scan across a row, we see that those arrows are now going up, and we've got 0, 1, 2, 3, 0. We've got the response function that's been flipped in that independent variable. And so that is just a consequence of the matrix vector multiplication. And if we want to find the value at just one output point and just there, then we need to flip that response function and do a scalar product. And you're welcome to do that. It's perfectly correct to do it. But also I would say it's perfectly correct to do the version I just showed you, which was to do the weighted set of columns, and then you don't do any reversing of any response functions. It's just a weighted collection. And so if you look at this expression, which tells us how to find g at position x equals 3, sure enough it says take f of k, so that's scanning down that input vector, and multiply it by each of the points in that row of the matrix. And you can see here that we've got a minus k here as we do that, and so that's where that kind of reversal comes from. And then it's got a plus 3. And because we've now reversed in that domain, that means the plus 3 actually shifts it now in this time towards the right-hand side. And so I'm just emphasizing there that that is a scalar product of 2 vectors. So both of those interpretations are perfectly valid. I would possibly say that for imaging systems, the first method I've shown you, the weighted sum of columns, is probably the only way of understanding it for imaging systems. For time-based systems, for like rolling averages that you might see later on with convolutions, this way of evaluating it in terms of reversing the kernel is perfectly valid and maybe more meaningful. It depends on the context. And also to note that if your kernel is symmetric, then this kind of flipping is almost invisible, because if it's symmetric in the x-axis, then it will look the same when you flip it. And that's why here I've deliberately used an asymmetric response function. Okay, and so if we do that, then we can write this matrix vector multiplication as just saying we've got an output vector g, which is equal to some matrix, capital H, times some input vector f. And so that's a very compact notation, and we're just understanding that that matrix H is just composed of shifted copies of the response function. And so that's why this is the kind of final slide. I just want to finish on that simpler version where we're just saying that to evaluate the output vector g, all we do is just visit each of the input samples in the input vector f, take each of those values and view it as a weighting factor for each of the columns. So for this third column here, I would be weighting it by a factor of 7. For the first column, I'd weight it by 5. Second column, I'd weight it by 3. And the latter two columns, I'd weight by 1 and by 2. And then I sum them all together to get the overall output G. So in review then, we've just looked at a 1D signal example for understanding 1D convolution. And using matrix vector notation is actually very useful for understanding convolution because it allows you to understand it in the two different ways that are often taught. A lot of the time it's the scalar product that is taught, and unfortunately people end up not very clear about what convolution is doing because they feel like they've got to reverse the kernel and so on. And you can do it that way. But I just encourage you to think about it in that simple way of just saying it's a weighted collection of shifted impulse response functions or shifted point spread functions. So thank you for listening.